First thing I want to remind everyone about is that, again, please do your course evaluations. evals.mcmaster.ca. So please do them. Feedback that not only I value, but Dr. Felipe, my boss, values, the dean values. It matters a lot. So please do them. I mean, honestly, like, the course, the number that matters the most is the response to the, like, I think it's question 3 or maybe question 5, the one where it asks about the professor, effectiveness of the professor. That one number gets, like, shunted right up the line. So profs who do really, really well get a special recognition from the dean, and profs who do really, really badly have to write a letter to the dean about what they need to do to improve. I'm not kidding. So that one number is actually, just keep that in mind for all of your courses, good or bad, that number is really important.
Yeah.
I'm not saying what you have to do with that number. That number is important. For me, the comments are really important. They're really helpful in helping me change the course and improve it. And as long as they're constructive comments. Yeah, in 2G last year, one of the TAs got the comment that she was really hot and we should have more TAs like her. Not sure that was really a constructive comment. Anyway, I'm not putting that on tape.
Oh, it's not good.
Okay, so today we're going to do a little bit of practice with Scale Up, and we might start talking about a little bit about instrumentation. The last topic we're really going to cover is sterilization. So we should be able to get to sterilization by Wednesday at latest, maybe even by tonight, which will leave the last Monday classes for review, which should be good. Yeah.
Do we have an assignment 4?
Yes, so that was the other thing I was going to mention is that I hopefully this afternoon will be posting an assignment 4. And now the question is, because possibly by tonight, possibly by Wednesday, you'll have all the information that you need to finish the assignment 4. The question is, when do you want to hand in the assignment 4? So I'm hearing some exam. The exam day is right at the end. You might want to hand it in before that.
Put it in a Dropbox.
Yeah.
How about like a week before the exam, and then we have
We
that
have like
week
a
to-
break from like the 8th to the 15th for like most of us here.
So I'm like, yeah.
So
Most of us.
like the 12th or something like that.
Check.
I don't know what day of the week that is. Is that the Friday?
That's
It's a
Okay,
Saturday.
not a Sunday. Is it 13th? Is that a Monday? No,
No,
that's
that's
the
a
Sunday.
Sunday.
It's the
Saturday.
7th is the Monday.
7th is Monday.
So the,
The 11th is Friday.
do you want the 11th or the 14th?
4G.
14th? Write that down.
Yeah.
So, the other question is, would you prefer to like scan it and hand it in electronically on a Dropbox, or would you prefer to just come in and hand it in the Dropbox in person? On Avenue, I could make an electronic Dropbox very easily.
Yeah, as long as it's okay to hand
That's
it
probably
by hand as well.
Can we do either?
Yeah.
Before people just
Yeah.
email to Ted or something? If
Yeah.
it can be either.
Yeah, that's fine with, it should be fine with Pick, it should be fine with me. It's a little bit easier for grading to have a hard copy, but when it's in the middle of exams, not everyone's gonna wanna necessarily come in just to read. The other thing I could do, depending on, I mean, we'll have a review session for sure before the end of class. But if you wanted, I could try and find a room to do a review session on the day the assignment is due.
I'll be gone.
So not the 14th.
Friday.
Because that whole week off, a bunch of us have off.
Yeah, so if you're off, then might as well allow the electronic Dropbox on Avenue.
Yeah.
Then
We all put
it
it
allows
easier,
flexibility.
Can we do it the Monday, like the day before the exam? Like I know it's like the day before, but it would be good because we all have that week off.
Yeah, the 21st.
Or most of us.
The 21st?
So then we can study that week and then we can ask questions.
We have exam on the 19th. on the Saturday, we have a 3D exam, and then we have Sunday, Monday, and then Tuesday.
Monday.
Wait, it's 20?
Or Sunday. Or Sunday, but like.
Check.
It's
So
not
we're-
Sunday. Monday, the 20th.
It's the 21st.
Yeah, I can't promise that it'll be me, it might be Tech,
Oh,
but we can have a review session sometime on Monday, probably Monday afternoon, and I'll look for Okay, yeah. So the question was, do I know when you're getting the midterms back? I actually have the midterms, I just haven't had a chance to check through them at all. But probably this afternoon. Yeah, probably this afternoon.
How did everyone do in the group take group one? Was it like 99 average again?
Very close. There are actually, although I have to say there are actually 1 or 2 people who did better on their individual one than they did on the group one.
Stupid groups.
Hey,
Just 1 or 2.
hey.
So on the whole, the groups were
Wait, was it?
very good. Okay, any other housekeeping type questions? Things that you want to chat about? Okay. So we were talking about scale up, and we talked about what were some of the things that you suggested as things you might want to base the scale up on last class.
Actually, I have a really quick question for
Yeah.
you, sir. For the paper assignment,
Yes.
what do you recommend so do you have to have other references apart from the one that we,
I
Are reading?
recommend it.
so when we write out 500 words,
It doesn't have good references.
that doesn't include?
Yeah, so your 2 pages doesn't have to include references.
Yeah, but
You can do that on top of the,
But if there's like an idea that we're taking from another reference that they had sourced maybe, so we should put that in?
yeah, or if there's subsequent papers that you think discovered new important things based on the original paper,
Okay.
then you absolutely can and probably should reference those.
So is that the main focus, it's not the summary part of it that is
So the
focus?
summary part is important because you have to explain what the paper is about.
Okay.
And without explaining, but remember, it's sort of to your boss. So you're not doing it at a high technical level. You don't have to go into to the details of it. You shouldn't be putting equations in it, for example. But you should be, if equations are an important part of it, then you should be explaining the consequence of the equations. And then you say, and then I would spend at least a page on the actual summary of the 2 pages that you have. Like half of your space on explaining the paper at least.
Okay.
But then probably about another half of the paper talking about what the significance was and what it led to.
But it's only 500 words?
Yeah.
Okay.
Yeah, so it's not a lot of space,
Yeah.
so you really have to pick on what the important findings were from the paper.
Okay.
And you don't have to share, you will not get a high grade if you say figure 1 showed this, figure
Yeah.
2 showed that.
Are you marking those or
Yes,
is,
I am.
or is
I am marking those. So that's my, I think Tick's head might explode if I shouldn't say that on tape.
Is there a rubric for it?
No, it's I haven't actually made a rubric
That's
for
just
it.
discussion.
Probably should, but it's based on how well it's explained and how thoroughly you've analyzed the consequences of it.
How well she likes you.
No.
Yeah.
How fast you can shave that mustache off.
Oh, no.
Ouch.
That's bonus points now.
Ouch. It's a low blow. November's almost over.
So
Yeah.
stop
Actually, I
it
have a
there.
question. Regarding all the things that we've talked about after refunds and multi-stage, are there any more calculations beyond multi-stage hemostats, like with scale up and everything? Are there?
So we're gonna go through an example of calculations for scale up in very shortly. And then there will be some calculations involved with sterilization.
Okay.
Yeah. Any other questions? Okay, so what we're getting back to where I was, what were some of the things that people thought you might want to base your scale up on? I remember someone said power.
Power to volume ratio is question mark.
Yeah. So, power to volume ratio. Okay, what else did people say last time? Or can you think of now? Yeah.
Fouling. So minimizing the fouling.
I'm gonna put that in brackets, and I'll tell you why, but it's a good idea.
Because it's well, heat transfer, I guess. It's part of ensuring that your heat transfer is good.
Yeah, okay. I'll explain why it's put in brackets, but yeah. What other thoughts? What are other ways?
Surface area to volume.
Sorry?
Surface area to volume.
So surface area to volume is almost impossible to scale up for if you're making it geometrically similar. Like if you still want to have a cylindrical bioreactor and you want it to go from 10 liters to 10,000 liters, we'll actually see in an example how it won't scale. The only way to keep that constant is if your scale up involves 10,000 1-liter bioreactors. So that's not one that it's,
Okay.
I mean, in some cases, that's the only way to do it, but it's not an ideal way, yeah.
You can scale it to keep the shear stress constant.
So, if you have shear sensitive cells, shear stress might be a way that you scale up.
We talked about the product to waste ratio, and that how if you increase it, there are times where you can produce more waste. There's a larger amount of whatever you're working with.
Yeah, I mean, that's definitely something that you ideally want to scale up for. And I'll tell you in a second when I'm putting it in practice. It is, I mean, ideally, that would be what you scale up for.
Can you increase the surface area to volume ratio by adding more surface area inside the reactor for cells to grow in? So like
Well,
vacuums, but
if you really want to have immobilized cells, there are actually specific ways that you can immobilize cells, and we talked about
Yeah, we talked about the encapsulation.
the different ways that you can immobilize cells. So if doing that is actually what you want, and you want your cells to be immobilized on a surface, then there are some really good ways of doing that. And there you would keep your surface area to cell ratio at least the same. Yeah. Any other thoughts? So cells depend on what to live? Yes, substrate. So you definitely want your amount of substrate to be the same. So we talked. Yep.
Would you want to keep your elemental composition of the media the same then?
So you basically want to keep your media the same. Yeah. But what else do they depend on to live? pH. Yeah. I'll put that in. Oh, I heard it. Oxygen. So the amount of oxygen you have. So, and maybe stirring. So you like the way the cells are being mixed in your reactor, and you want them to be mixed about the same. Okay, so constant power input, constant power to volume ratio. It actually does imply about or a very similar O2 transfer rate, which is kind of a handy thing. So if you've got the same amount of mixing per volume, the same amount of power put in per volume, you'll probably have a very similar oxygen transfer rate, which is kind of cool, to keep your cells happy and alive. And that is, power is, there we go. Okay, so your N is how fast it's spinning.
So power is equal to that equation?
Yeah,
Is that a D time squared or D, what's the?
dt squared. So this is the diameter of the tank.
Is dt one term or is it two?
It's one term, that's a little subscript. dt. Okay. Look at that. exactly the right definition. Oops, I'm looking at the wrong one. And it is agitator speed in RPM. Okay, so how fast is your agitator spinning around is your N. Okay, so let me just double check that I'm correct on that. Yep. Yeah, so how big your tank is squared times how fast your agitator is spinning cubed gives you the power.
How can you neglect like all the, everything about the agitator though? Like,
So that's your, it's not, that doesn't actually give you the power, but that gives you the scale up ratio.
gotcha.
So your scale up ratio will depend on N cubed times dt squared. So we'll see in a second, why don't we talk about stirring? So stirring will depend on, you know, basically your scale up there would be a constant Reynolds number. Okay, and your Reynolds number is NDI squared. Oh, should I pick the wrong I? Hold on, this might be I. Let me just double check, I'm really sorry about that.
Would be powered.
I'm just checking, I think it is tank. Let me just check. Yep. Yeah, it is tank. Okay, I just wanted to double check. It is tank. Okay. And Reynolds number is also tank. ET squared, rho over mu, right? So that's the density of your fluid, that's the viscosity of your fluid. But when you go to scale up, what you actually care about is the N dt squared, because your fluid properties will be the same in a scaled up reactor. I mean, technically they might not be exactly the same if you've got a different cell density, but they'll be about, your goal is for them to be the same. So when you're doing a scale up ratio, you need to keep those numbers the same if you've got a constant Reynolds number. So the constant Reynolds number gives basically the same mixing. So if you're happy with how your cells are going through the reactor, if you keep a constant Reynolds number, they'll keep going through the reactor about the same way. Now that may not be what you want. We want a constant shear. The way you do that is constant speed at the impeller tip. And that's N times DI, where that's the impeller diameter. Okay. If you had constant impeller rotation number, which is just N, then you'd have constant mixing times. Yeah.
What are all these equal to?
The NDI business.
Yeah, or like NDT, like is that equal to power? So the top one is equal to
So it's
power?
not actually equal to power, but it's the input that will change in a scaled up reactor. So all your other things that affect power will stay constant because you've got constant fluid and all of that stays constant. So when you're actually going to scale up, what you're trying to do is keep this number the same despite the fact that you have a bigger reactor. Okay, so if you're scaling up based on constant power to volume ratio, which then implies oxygen transfer rate, and you want to keep that oxygen transfer rate about the same, you look at what your N cubed dt squared number is for your small reactor, and when you scale up to a big reactor, your diameter will change, And then what you figure out is what is the new agitator speed you need in your bigger reactor to keep your power to volume ratio the same. Everyone's got that now?
Yes.
Okay, I realized I just kind of threw that out there. Didn't explain it super well the first time. Okay, so same thing if you wanted constant stirring, N times dt squared. You'd figure out what that was for your happy small reactor, and then keep that number constant for your much larger scaled up reactor where you have a larger diameter.
Is that DI or DT?
This one is dt.
Is it multiplied by rho mu, or is that mu?
So if you actually, in this case, the actual Reynolds number is n dt squared rho over mu,
Yeah,
but rho over mu is going to stay constant in your scaled up reactor, so you don't actually need to know those in order to scale up your system based on constant Reynolds number. Everyone's got that? Okay, so obviously if you're scaling up based on constant shear stress, then you'll have a very different effect on your power to volume ratio, right? If you're keeping this number constant, that number is going to change quite a bit, right? So not all of your effects are going to scale the same way. So what that's saying is that you can't just take a small reactor, scale it up to a really big reactor, and have everything stay the same. Like Carl was talking about, could you keep your surface area to volume ratio the same? Well, the only way to do that effectively in cylindrical reactors is to have lots and lots and lots of little cylindrical reactors. And the idea is that you want to scale it up to a really big reactor, which is much more efficient. So in some cases, you cannot scale things if you're going to a big reactor. And then the question is, where are your priorities? Because taking one of these things as a priority is going to have an effect that may be detrimental on other priorities. So if you're keeping your oxygen transfer rate the same, you may find that your shear stress goes way up for your cells. So it always is a balance, and that's why it's a somewhat empirical thing. And for some cells, different rules work better in scaling up than others. Does that make sense? Okay. Yeah, the other thing to keep in mind, so for example, if you're, and then why did I leave these in brackets? These are things that are actually very difficult to control and to know in your design what the consequence will be. So another one, for example, is, I want to say bubbling, but I'm losing it, foaming. So say you don't want much, you want sort of the same amount or not much foaming. If you're trying to scale for foaming, it's very difficult to predict how much foaming you're going to get in a new reactor configuration. So we don't have quantitative ways that we know that if we change this, it'll have this effect on foaming. So foaming is like that, fouling is like that. You know, you can have general rules for what you think it'll be like, but it won't necessarily. And product to waste ratio is another one of those things that is very difficult to quantitatively predict based on a new scale-up factor. There's no nice NDI scale-up factor for product to waste ratio. It's not a nice, easy relationship that you can easily predict. You have to go and try the reactor and see what happens, unfortunately, because cells are complicated, and we don't know everything about cells. So maybe if there's a day when synthetic biology comes a long way and we actually can model every little biochemical system within the cell and how it responds to different stresses, perhaps you could come to a point where you could predict the outcome in those things, but it would be incredibly nonlinear and very, very difficult to predict because cells are incredibly nonlinear control systems that are very complex. And most of the time we don't know exactly what the response is to different situations. But there are some things you can sort of think about. And the problem is getting it right is wrong is even more expensive. So as you go to making bigger and bigger reactors, the expense involved gets bigger and bigger and bigger. Okay, so say we wanted to keep oxygen transfer the same. I said power to volume ratio is a way that you could keep it the same. So the power to volume ratio basically is from agitation. So if you're increasing your tank diameter, you're going to actually have to reduce your agitator speed, right, to get the same power to volume ratio. So you're going to have less agitation, and there there's a chance you'll have poor mixing if you go too low. And then the other way that you can increase it is you increase your aeration. If you have too much agitation, we know that there's too much shear stress, so you get cell damage. If you have too little aeration, what happens? Too little aeration and too little mixing, what's going to happen? Yeah, so O2 limitation. In fact, if you have higher oxygen but still not enough aeration, you actually end up having CO2 buildup, which is also difficult on the cells. Here, if you have too much aeration, that's when you have foaming occur as well. So your actual place that your cells are happy is somewhere in this happy spot between too much and too little agitation and too much and too little aeration. And it's not well quantified what that is. You probably, with a particular cell type, you may be able to find out what your shear stress limits are, so predict this upper level. But down here, maybe by looking at your Reynolds numbers, you can find out what the limit of core mixing is. So as long as it's good enough, you have a good enough mixing, you may be able to predict it based on that. But foaming, not easy to predict. CO2 effects, again, not entirely easy to predict, especially when we're looking at KLAs with your, because your KLA is really what's keeping your cells happy in the middle here. Not easy, we talked about how it's not easy to predict KLAs when you've got cells there, and you have to actually do experiments to figure out what it's going to be. Okay. So let's do a little example. So this is example, I'll go over here. Look at this big eraser. Oh my goodness. It goes so fast. And it's actually here. It's like a miracle. So example 10.2 is from your textbook. Okay, and what it reads is, after batch fermentation, the system is dismantled and approximately 75% of the cell mass is suspended in the liquid phase. And the liquid phase is 2 liters. Okay, and 25% is attached to the walls and internals in a thick film. So interestingly, they've done work with radioactive tracers, and it shows 50% of product is associated with each cell fraction. So it's intracellular product. So this is where Carl's question about surface to volume ratio is important, because although only 25% of your cells are on the walls, it's still making half the product. So in that case, You might want to examine going to an immobilized cell system because it might be way more productive. But if you're just going to a straight scale up, then you're not really recognizing that, you know, no one's actually done that experiment to see how much of the product is coming from the cells that are fouling the reactor, that are immobilized on the walls. You might not realize the effect that it's going to have on scale up, changing your surface to volume ratio. Okay, so productivity is 2 grams product per 2 liter reactor. Okay, or 2 grams product per liter in the reactor, so in other words, it's making 4 grams. And it's asking what would be if you scaled it up to a 20,000 liter reactor, what would be your productivity if height to diameter ratio was maintained at 2 to 1?
That means 2 grams of product per 2 liters.
Nope, that's not a 2, that's an L per liter. So you have a 2 liter reactor, and that would be, it would make 4 grams. Okay, any questions about the example? That makes sense? So what I want you to do is try and figure out what your new productivity would be. Basically, qualitatively, now you're gonna have a lot less walls and a lot more liquid. So what you're gonna have to do is figure out how many liters of liquid and how many square centimeters of walls you're gonna have compared to in your scaled up reactor compared to your small reactor.
Are the reactors like cylinders?
So they're cylinders with a height to diameter ratio of 2 to 1.